Greetings everyone, I'm Nenad Petrovic, a teaching assistant at the Faculty of Electronic Engineering, University of Niš in Serbia, the Department of Computer Science. Now, I will present you our paper entitled GPU-enabled simulation of a combined macrodiversity system in gamma shadow Nakagami-m fading channel. In a gamma shadow Nakagami-m fading wireless channel, on its way between a transmitter and the receiver, the signal is spread out into multiple components that travel along different paths. This causes a substantial signal degrading effect, commonly known as fading. Another degrading effect, known as shadowing, causes power variation in a signal envelope. The short-term fading, also called multipath fading, causes signal envelope variation. A long-term fading can be modeled with gamma distribution or long normal distribution. To mitigate the effects of both long-term and short-term fading on the performances in cellular mobile radio systems, a microdiversity receiver is utilized. Microdiversity systems can reduce the impact of fast fading, while on the other side, macrodiversity system reduces shadowing effects. In wireless channels, where there is no optical visibility between the transmitter and receiver, and the signal is affected by fading, there are no conditions for formation of a dominant component. Then, Nakagami-m distribution is successfully used to describe the signal propagation. Nakagami-m distribution is generalized distribution characterized by two non-negative parameters, m that controls the shape of distribution and omega which represents the mean power. In this paper, we propose the combined diversity receiver consisting of macrodiversity selection combining receiver and two microdiversity maximum ratio combining receivers. Mobile signal undergoes in a cellular mobile radio gamma shadow channel with a short-term Nakagami-m fading. By varying Nakagami-m short-term fading severity parameter m and the order of gamma distribution c, we have considered and discarded change in system performances and graphically represented numerical results for the moment generating function. Moreover, we integrate the obtained formulas within the simulation environment for optimal network planning, leveraging general purpose computation on GPU for faster execution. On this slide, the illustration of the proposed system is given. In what follows, I will show you the derivation of moment generating function expression. The signal envelopes have Nakagami-m distribution, as you can see in the equation 1. Here, gamma m is gamma function, while m is Nakagami-m short-term fading severity parameter, and omega is the power of the desired signal, respectively. After transformation, the probability density function of the signal x becomes as given in equation 2. Moment generating function in case of branches at the output of the microdiversity maximum ratio combining receiver will be as given in equation 3. In a gamma shadow channel, the random variables omega 1 and omega 2 are gamma distributed. Here, c is the order of gamma distribution, while omega 0 denotes the mean value of omega 1 and omega 2, while ρ represents the correlation coefficient. At the output of the macrodiversity selection combining receiver, the moment generating function of the signal is given by the equation 5. On this slide, it is depicted how moment generating function derived in the equation 5 changes for different values of the parameters m, c, and ρ. It can be observed that for the increase of fading parameter m and parameter c, the decrease of moment generating function will be achieved, which has a positive effect on overall system performance. Another effect is that higher values of fading parameter m affect the moment generating function more intensively. As a result of the combined effects of the observed parameters, it is noted that the correlation coefficient ρ exhibits higher influence on moment generation function for higher values of Nakagami-m severity parameter m and higher values of gamma long-term fading severity parameter. Now let's take a look at the modeling and simulation environment. First, the user has to provide a smart city model in terms of service consumers, providers such as base stations, and communication channel characteristics. After that, the proposed model is transferred to fading calculation, which is GPU enabled and is used in order to calculate the quality of service parameter values. Finally, it is forwarded to linear optimization procedure that actually calculates optimal values that will be used within the commands for software-defined radio base stations. For linear optimization, AMPL and CPLEX were used. The modeling and simulation environment is run in a web browser. It was implemented using JavaScript and 3JS library for 3D graphics. As you can see in this picture, it mainly aims smart city scenarios. Here, the autonomous vehicles represent service consumers, while the antenna represents a service provider. When it comes to fading calculation, general-purpose GPU programming approach was adopted in order to speed up the calculations. It was approved as an effective approach in many published works before. It was around 25 times faster than our previous work from reference number 15 and around 38 times faster than similar system with 3 Macrodiversity maximal ratio combining receivers from the reference number 18. Finally, you can see CUDA-enabled C code, which is actually the implementation of fading calculation procedure, which is later used for quality of service value determination. Now let's sum up. The analysis presented in this paper referred to the scenario of a cellular mobile radio system where the signal undergoes gamma long-term fading and Nakagami-m short-term fading on the other side. Combined macrodiversity system with 1 microdiversity selection combining receiver and 2 microdiversity maximal ratio combining receivers has been proposed to minimize the effects of this fading channel. The expression for moment-generating function of the signal at the outputs of microdiversity maximal ratio combining receivers has been derived and used to obtain the closed-form expression for moment-generating function of macrodiversity selection combining receivers output. And finally, the derived formulas are integrated within the software modeling and simulation environment, aiming optimal network resource planning. Within the simulation environment, general-purpose GPU programming approach is used to speed up the calculations of fading effect and has proven to be a powerful approach in this kind of analysis. Thank you for your attention. This work has been supported by the Ministry of Education, Science and Technological Development of the Republic of Serbia.